And so now we need to talk about some modifications to our ideas of momentum and energy for when we're dealing with special relativity, when we're dealing with particles that are moving at or very close to the speed of light. So in order to account for conservation of momentum in all of our inertial reference frames, so remember for Newtonian mechanics, right, our conservation of momentum says that, we define momentum as mass times velocity. And so if we have a collision or an interaction where the net force on any individual object comes from the other one, then our momentum is conserved. The total momentum of our system stays the same. Now, we need to modify this definition of momentum for when we're dealing with objects at or close to the speed of light. So relativistic momentum, right? Again, when objects are moving at or close to the speed of light, now we're going to define momentum as gamma mv. So we're just modifying it by this factor of gamma, right? And remember that our gamma is 1 over the square root of 1 minus v squared over c squared, where v is the speed or the velocity of the object that's moving. Its mass is m, measured by an observer that is at rest with respect to the mass, right? So m is measured by the person holding the object. And then v is the speed of the object. And now notice that when our speed of our object is much less than the speed of light, then this term essentially becomes 0 and gamma is equal to 1. So if your speed of your object is sort of normal speeds, everyday life speeds, then this equation reduces to the familiar one that we already know. Now we also have to account for relative velocities in special relativity, right? So when things are moving reasonably slow, right, normal everyday speeds, we learned in physics 1 that if I have two observers, observer A and observer B, right? And so person A is moving relative to the Earth. Person B is in a reference frame also that is moving relative to the Earth. And then E is our stationary reference frame, meaning it's stationary relative to the Earth, right? So I have my two observers. And we know from physics 1 that the velocity of some object A, with respect to the stationary Earth is going to equal the velocity of object A relative to object B plus the velocity of B relative to our stationary Earth. And these are vector equations. So this is what we learned in physics 1 for relative velocities. But now it turns out if these speeds are at or near the speed of light, again, we need to modify our relative velocity equations. So for our relativistic definitions of relating these velocity measurements, then I have the velocity of A relative to B is going to equal velocity of A relative to the Earth minus the velocity of B relative to the Earth. And that is just, right, this solving for here. But we have to modify it for special relativity. And so then that's going to be over 1 minus those two multiplying by each other, right? VA E times VBE, and we want the absolute value of those divided by C squared. And that goes on the bottom of our fraction. So we have to modify our normal equation, right, with a relativistic term. And we can do the same thing if we wanted to know, right, the velocity of A, if we wanted to solve this for this one, for this one, then this equation just becomes, right, what we had already, but again, we are modifying it with our relativistic term. In the denominator of our fraction. Now, finally, we have to modify how we think about energy, right? So in sort of general Newtonian mechanics, kinetic energy, right, is half mv squared, right? That's our standard definition for kinetic energy from Physics 1. But in relativistic mechanics, we need to modify this again. So our relativistic kinetic energy, we're going to write our kinetic energy equation as gamma mc squared minus mc squared. So our total energy is going to be our kinetic energy, right, which is our half mv squared, is going to equal, this is our total energy. And again, our gamma term is just relating to the speed of light. So this term mc squared is called the rest energy, or, right, ER for rest energy, and that's just mc squared. And that's our sort of our famous Einstein equation, right? E equals mc squared. Now, this is not what he won the Nobel Prize for, but this is the common thing that people think of when they think of Einstein. And then our total energy, right, E total, is our gamma mc squared. And so we can rearrange this equation and say that our total energy is going to equal our rest energy plus the kinetic energy, right? Or mc squared plus half mv squared. And again, our total energy, that's our gamma mc squared. Now, one thing that this equation tells us is that rest energy means that objects or particles have energy just because they have mass, right? This is what we mean when we say that we have a mass energy equivalence, right? So the mass of a particle can be completely converted into energy. You can also convert energy into particles, and this has been done to subatomic particles in, very large particle accelerators like the Large Hadron Collider, the LHC, in Europe. Now, we can also relate momentum and energy together, right? So our total energy squared, right? So this E here is our total energy. So this is my total energy. Is going to equal momentum squared times c squared plus our rest energy, mc squared, right? And again, this mc squared is our rest energy. And so this equation lets us relate momentum and total energy of the particle. Now, when the particle is at rest, right, then this term is equal to 0, and then you have E equals mc squared. When the particle is moving, right, then you have to account for also its momentum. And this also lets us, this fact, right, that if a particle is at rest, then E equals mc squared, lets us express mass in energy units. And the energy unit of mass is the electron volt. Often we use mega electron volts, or times mega electron volts, meaning 1 electron volt times 10 to the 6th, right? So the mass of an electron in this, which we know is 9.11 times 10 to the minus 31 kilograms, is equal to 0.511 mega electron volts, or 0.511 times 10 to the 6th electron volts. We can also put this in terms of atomic mass units. So one atomic mass unit is 931.494 MeVs, mega electron volts per C squared, right? Because again, we're just E equals mc squaring that. Now, this brings us to the other thing that Einstein is famous for, which is general relativity. So special relativity is just dealing with essentially the speeds of objects, right? The speeds of objects that are moving at or near the speed of light. Now, general relativity takes this and sort of extends it to mass and gravity as well. So we know from Newton that mass exerts a gravitational attraction on every other mass, right? And that Newton's law of gravity says that the gravitational attraction between two objects is equal to our gravitational constant g times the masses of our two objects divided by the distance between them squared. All right, this is our familiar form of Newtonian gravity. Now, we also know from Newton's second law that the net force on an object is equal to mass times acceleration. And these two forms of mass are not necessarily the same, but you can think of mass in terms of gravity, or you can think of mass in terms of inertia. And this value of big G for our gravitational constant here was chosen to make those two masses be the same. And Einstein reasoned that the inertial and gravitational mass are indistinguishable, right, from each other. That the mass, inertial mass and gravitational mass are essentially the same, and there's no experiment that you can do to distinguish between the two kinds of mass, between inertial mass and gravitational mass. And this leads us to our postulates of general relativity. And general relativity says that, again, similar to our special relativity postulate, is that all of the laws of nature, not just mechanics, but all of the laws of nature, have to have the same form for observers in any frame of reference, whether that reference frame is accelerated or not, right? So Galilean relativity only referred to inertial reference frames, meaning reference frames that were not accelerating. General relativity says, no, it doesn't matter. You can be accelerating, you can be moving at a constant velocity, you can be at rest relative to something. And everybody is going to agree that physics works no matter what they're doing. The other postulate of general relativity says that you can't tell the difference between gravity and acceleration, right? That at any location in space, a gravitational field is the same as being accelerated. And this is called the principle of equivalence, that you can't tell the difference between being attracted to something gravitationally and just any other kind of acceleration. That there's no experiment that you can do to distinguish between those two things. And this leads to some interesting consequences. One, gravitational mass and inertial mass, completely equivalent. They are the same thing, right? So these two masses, two different kinds of mass, are the same. Two, if you put a clock, so not only is a clock that's moving very quickly going to run slower relative to a stationary observer, right? Or a stationary observer will measure a moving clock to run slower. A clock in the presence of a large gravitational force is going to also run slower than one in a location where the gravitational force is negligible. So if you take a clock and have it on the Earth, and then you take another clock and put it very near the sun, the one that's near the sun will run slower when you bring them back together than the one that didn't go near the sun. The frequencies of radiation emitted by atoms in a strong gravitational field are going to be shifted to lower frequencies. Basically, there is a gravitational Doppler shift. So if you remember from Physics 1, when you learned about sound waves, you should have learned about Doppler shift, right? When something is traveling towards you, you're going to perceive a higher frequency, and when something is traveling away from you, you're going to perceive a lower frequency. Gravity does the same. Now, this also works for light. Sources of light that are moving towards you, you will perceive that the light that you see in your eyes as a higher frequency, as bluer. And if a source of light is moving away from you, then you will see that light as at a lower frequency, or redder. Gravity does the same thing. That if you have a source of light that is in a large gravitational field, there's essentially this gravitational Doppler shift, and that's going to shift those frequencies, observed frequencies, to lower frequencies, to redder colors. And this has been observed by astronomers. You can also, another consequence of this, is that you can transform away a gravitational field if you choose an appropriate acceleration. What this means is that you can't tell the difference between free fall and zero gravity. There is no measurable difference between an object in free fall and an object away from any sources of gravity. And Einstein specified a quantity called the curvature of space-time that describes this gravitational effect at every point. And so a good summary of this was made by John Wheeler in the late 1970s, where he said that the way space-time works is that mass 1, some large source of mass, tells space-time how to curve. And then this curved space-time tells other mass how to move. So general relativity makes some predictions. One prediction is that if you have some source of light back here, and that light, in order to get to us on the Earth, if that light has to pass by a big mass, something with a lot of gravity, like the sun, that light is going to get bent. And so what we're going to see is we're going to perceive that instead of this star that we're trying to look at being back here, which is its actual location, we're going to perceive that it's over there. And this is a measurable effect. This has been measured during total solar eclipses a lot of times since 1917-ish, which is when this was first verified. General relativity explains discrepancies in Mercury's orbit. And it also explains predicts the presence of black holes, which have been observed and which have been, at this point now, actually photographed, which I think is very, very cool. And so next time we're going to talk about some other things. We're going to talk about photoelectric effect and quantization and the beginnings of quantum physics.